Right. So let's continue, and we're explaining the Thom-Pointryagin construction, the Pointryagin theory. So the main thing that we try to understand is how do you use this very simple fact that if you look at one-dimensional manifold, they are just either circle or interval and union of those. The nice property is there's no boundary in the circle case. In the two boundary, but they are in different orientations. So the number of the point and the boundary altogether is always 0. Just this fact. Let's just try to see how do you use that. Okay. So the first thing we use is to have a well-defined degree. So it says that if you have two manifolds of the same dimensions, and take a look at any map. Okay. So look at the pre-image of a point, and then you count the number. That's called a degree. So first of all, you have to use the SAS theorem. Says that most of the points in the target are good points, so the regular points. Okay. So you choose one of those good points, and then you look at the pre-image and count the number with orientation. So there are two issues that you can change the point or you can change the map up to homotopy, but they are all changing in a one-parameter direction family. And this is the thing of saying that if you're moving in one-dimensional family, look at the endpoint, and then the number has no contribution for the whole interval. So therefore, you get a well-defined map called a degree map. Okay, and one of the things that we would prove you today is this statement that if you look at the sphere, the target is a sphere, that this map degree is really in fact isomorphism. It's a more interesting statement now, right? It's just a map, but this map is really injective and surjective. Okay? So that would be the Pointryagin theory that we'll be explaining. Before we do that, we're discussing a very interesting theorem called the Poincaré-Hopf theorem. Is that if you have a vector field on X, so and the index is independent of V, and so if X is some space, we're just drawing some part of it. We are thinking, if you are saying that X is always a closed manifold without boundary. Okay? So let's say this is part of X. A vector field meaning that at each point you have a tangent vector. So some of the tangent vector could be 0. Okay? Okay? So this is maybe 0. So this point, the vector field will be 0. Okay? And if you're at a particular point which is the vector field is 0, let's say this is one of the points. So there are various generalizations where the critical points may be not isolated and so on. So we are assuming the simplest case to illustrate the main point. So let's say one of the points where this point, the vector field is 0. And let's say this is isolated 0. So all the nearby one is not 0. So draw a very small circle. So this is, say, n dimensions. Okay. So draw a very small circle around here. So this is a small ball of dimension n, a very tiny one with this as the origin. So this one C. Okay. So all the other tangent vectors are not 0. Okay. So you take a look at those tangent vectors along the boundary. So some may be along this direction, along that direction, but they are never 0. So that could be here. Doesn't really matter. Okay. But this neighborhood, anyway, you look at the whole neighborhood, you can put it inside our end. Okay. So think about, we only look at it locally. So this is in our end. And then what do you get? You get a map. The vector field will get a map from the boundary, which is a sphere of n-1 dimensional, this one. Okay? And each of this one, the V will be a vector in our n. Okay? But it's not 0, so you can normalize it. So that will be a map to Sn-1. Okay? And that's what we call the index. So this is defined to be the degree of this map. Okay? So this is defined to be the degree of this map. Okay. From the neighborhood of a small neighborhood of one of the 0 set to all the possible directions. Okay, okay. It just says that you have a well-defined map for degree, and that's called the index. Okay. And how to prove that it's independent? That's what we try to prove. And we also show an interesting application last time, that using this you can show that this number is the number of triangle in the triangulations, right? Alternating number of triangles last time. Okay, so how do you prove that? So this, first I'm going to use this fact. Okay, so proof. Okay, step one. Okay. A priori, this may not look the same as that theorem, but that will be later. So, okay, let's say you are in a Rn. You have inside some particular space Rn already. Okay. You have some domain. So let's say this domain is Zn. So let's say, for example, it could be like this, or that, it doesn't matter. So the domain is this. Okay, so this domain has two swimming pools inside. Okay, so that's the domain. Okay. Now, let's say V is a vector field on the domain. Okay. So at each point you have some vector. Some could be 0 and some other vector. So you have some vector field on this whole domain with boundary. Yeah. All right. So how is using this? Okay. So you pick a particular direction. This is Sn, right? So you Rn. So you choose a particular direction. Call this V0. Okay. Fix a particular direction, Sn minus 1. Okay. So think about this as Rn. And then choose a particular direction of usually this direction as V0. Okay? And we look at a curve. So let's say this one is at that direction. Okay? So then look at the nearby one. Look at all those with this direction. Some may be shorter, some may be longer. We just look at those with those directions. Some could be 0, and some could be like that, like this. Okay? So in this particular case, this will be the path of the same dimension. Okay, that's it. Like gamma. Okay. So let's say gamma is a path inside C, okay, such that the V along, so this is the V, right? This is this fixed direction, V0. V along this whole gamma is, every point there is parallel to this V0. So this is a one-dimensional thing because this whole sphere is n-dimensioned. Imposing one of these conditions, and n-1 condition. So the number, all these are of the same direction will be one-dimensional space. Okay. So you look at that one-dimensional space. This is this, like that. Right? So this is the gamma. So all the vector field on that is all gamma. Another point is. If V along gamma is never 0, non-vanishing, then what happens? What happens is, think about this is gamma, for example. Okay, so if this is this direction, and then that has to be, can be shorter, can be longer, but they can never switch directions. Okay, if it's just 0. Then that's different. If it's just 0, then that can start to switch directions. Okay? If it's never 0, there's no way you can switch directions. Or you don't have to be that direction. I mean, it could even be up. So maybe just up. So you don't want to say that the vector field is along, is a tangent direction. So if this is like that, if it's never 0, this has to be always like that. Okay? But if it's 0, then it can start to switch directions. That's the same argument as arguing here. This is the same argument that we use here. Okay. If it's non-vanishing, then because parallel can be both directions. In both directions, I still call it parallel. Okay. If it's never vanished, then it never switch direction. Okay. not never switch direction. Switch direction. So this argument tells the following. Okay. The claim is if V is a vector field on Z, okay, let's say with isolated zero, okay, and you look at Z minus all the points which is 0. So you take away at each point which is 0, you remove the small ball around it. Then on here, V is never 0. Whenever 0, you take it away. Take away the whole neighborhood. Okay? So call this gamma 0 first. Okay? So like this. So originally, Z could be like this. Okay? You have some vector field. Okay. And this one would be at some point the vector field will be 0. Okay. But then I take away the neighborhood of those 0. Now the rest, V is never 0. Okay. So V is non-vanishing on the complement. Then we can use that argument. Okay. What is the argument? So let's assume it is vector field on this, which is pointing outward. On Z. Okay, here. Like this. Then this will tell us that there's no 0 here, and then the thing is then the degree of V, quotient of V star. For the boundary of that, the boundary of this to the sphere, and minus 1 is 0. Okay. This one has several boundary components. One is the original boundary component, and you have all these other smaller boundary components. Okay. And the reason is that inside, in the interior, there's no 0. And then you can never change sign, and then you can count the degree by the earlier definition. That would be the same. So that would be 0 because inside, yeah, because of this. Okay. But this boundary has several components. One is the original boundary, and then you add the other boundary for each 0 set. Okay. And it turned out that if you look at those small of that, the vector field on that, that is the definition of the V as 0. That's 0. But because you change the directions on the ball, and then the side, we get a different sign. Okay? So that becomes minus the index of V at those 0. Not quite P. Okay. So here the thing is we are assuming this one is pointing outward. What does this statement say? Okay. So this is this one. Okay. This is called the degree of the Gauss map. So, and this is one of the things that it does not really, because once you do that, because it's pointing outward, this is just a normal vector field, which is never zero. Okay. So this is what we usually call the Gauss map. Let's just put a remark here. So you take any oriented hypersurface, oriented meaning that at each point, the normal direction is one dimension, but you have two different directions. Okay, and oriented meaning you have a consistent way of choosing which one is outside, which one is inside. Okay, so then you have this. So and then you have this normal direction, and then you normalize this so that the length is 1. Okay, and this map is called a Gauss map, sometimes called G. And this is the thing that you learn in the very beginning of a differential geometry class. They give you the curvature and various other things. Okay? Well, so this is really depending on the hypersurface. Okay? And because the vector field is non-zero, always pointing outward, and this is just a Gauss map. This is just the normal direction. Okay? So it tells us that. So this is the claim. Let me finish that claim here. The one tells us that. If you have Rn, you have a domain here, Zn, and then if V is a vector field on Z, two property. First is pointing outward. Second is no condition, isolated zero. Okay, there's okay, so that's it. This is pointing outward essentially. Then you sum over all the index. So this is why I need to assume it's isolated. Otherwise, you have to do something clever to define that. Index of V as Z. Okay. Is equal to the degree of the Gauss map, which is only depending on the hypersurface. Okay. Or Gauss map. So the Gauss map is on the boundary of Z. Okay. So therefore, in particular, it's independent of the choice of vector field, as long as pointing outward. Okay. Still look very different because this is on a domain. This is an abstract closed manifold. And then how do we do that? Well, we can embed any closed manifold inside Rn. Okay? So that's the second thing we need to use. How do you use the embedding theorem? Okay? We always know that every manifold sits inside some big Rn. Here, eventually, it doesn't care which Rn you choose. It doesn't care how you sit inside. Okay? So here's how it's very clever, the argument. Okay. So now we're trying to apply this to an intrinsic case. So X is any closed manifold with V is some vector field on X, let's say isolated 0 or something. Okay. All right, so let's just draw part of it. So X is this, and then you have some vector field. The vector field may be this, could be 0 somewhere, could be this somewhere. So you have some vector field on X. Okay. You put it inside some big Rn, you don't really care. Anyway, you put it inside some gigantic Rn. Okay. And that. x inside somehow n. Yeah. And take a neighborhood. So Z is the neighborhood of x inside Rn. So this closure. So this is Z. Okay, it's a neighborhood. Well, you have to use this basic statement that the neighborhood is always look like the normal bundle. So this neighborhood field, this in fact will look like the normal bundle of x inside Rn, meaning that if you look at each point, so maybe I use the blue to indicate the vector field. The vector field is 0 here, the vector field is this. Okay. Now at each point, you look at the normal vector, and then locally, the normal vector is exactly filling up this space. Okay, so you can look at the whole neighborhood as a normal bundle of the space locally. All right. So this is the normal bundle. In particular, that is a bundle over X. Okay. Now we want a vector field on Z, though. I mean, we only have a vector field on X. Okay. So how do you define vector field on Z? Well, take a point here. Pick a point. A point here is a downstairs. You have a point X. Okay. And then this is a normal. This fiber is a normal bundle for X inside at the point X. That's it. You get the normal bundle at the point X. Okay. So take a vector here. Any vector, call it N. Okay. So upstairs is a point downstairs together with a point upstairs. This is a point. Point upstairs is this. This is N. Okay. Now we can define a vector field on Z at any point. Now we already have the vector field on X. Now we want to get a vector field on Z by just adding these two, and you get this vector at this point. At this one, and then that. Okay, so that would be this one. Okay. Call this V tilde. Okay. So. Define vector field V tilde on Z, which is the same as the normal bundle of X inside Rn, this neighborhood. So this vector field V tilde at a point is just the vector field X V at the point plus, we're treating all of this as a vector in Rn. Okay, plus this vector n. This is what I draw here. Okay. So if you just look at this point, this is this vector plus this vector, so this is V tilde. Now this has a property that when you restrict to X, it is original vector field because n is 0. Okay. Second, when you're at the boundary, it's always pointing outward. Because you're normal, n is pointing outward. Okay. This n is always pointing outward. So it's already pointing outward. It's like this. So this vector field, when you restrict to X, is exactly the original vector field. The second one is this one on Z is a point outward. It's always pointing outward. All right. Also, when is this 0? Well, first of all, this vector field is 0, n has to be 0. And also, V at that point has to be 0. Okay? Because they are linear, these two has to be linear independent anyway. Okay? So it's always so the first statement is V tilde at xn is 0 is exactly the same as those points in X. So the 0 set is exactly the same as the one on X already. Okay. All right. So, you really look at a vector field on different space. One is on X, one is on a bigger space. Okay. So therefore, when you compute the index, you have to compare the dv tilde at such a 0 at such a point. At such a point. Okay, we differentiate. Then you decompose it into two terms. One is the x direction, one is the normal direction. Okay. Because first of all, when you say 0, it's already on x. So the whole tangent space, which is Rn, is split into tangent space and normal space. Okay, so you just decompose this derivative in this two terms. Okay. The definition is just because the map is just v%. So this x direction is just dv, and there's no cross term. It's just this is identity because it's identity map, so it's identity. Okay. So whenever you want to do this kind of rotation, angle, or anything, on a bigger space or on a smaller space, it's really no different because the rest is just identity thing. Okay. This tells us that index of x tilde at this point, at such a point, is the same as the index of v at the point x, because just add something, nothing. So wonderful. Okay? And you're done. Because then this sum of this index become the thing that you think about on the z, and then it's just something independent. Okay. Then 5-1. We're done, please. Sum of, we are done. Okay, so I'm assuming that our critical points are isolated, and that this argument I'm assuming non-degenerate. So if it's not non-degenerate, you have to do some tilt a little bit, but that's essentially the key argument. Yeah, right? So again, if you look at any manifold now. So see, we have used two arguments. One is when you are inside Rn, you just use this one manifold has the sum of boundary point is 0. Okay? That was a homotopy argument. But then it's really on Rn thing. But on abstract manifold, then you have to do the embedding. But amazingly, it doesn't really matter how you do the embedding here. Of course, this is the argument here. The vector field is just V, but something normal, which is like identity thing on the other direction. So you don't really care. Okay? So take any vector field, the sum. Take any vector field, the sum of 0 basically is independent of the vector field. It's a topological statement called the error characteristic. All right? So there's this beautiful Poincare-Hopf field. All right? All right, so now it's coming back to understand, try to understand this. Okay. M to another space, and let's say of different dimension. Let's see. Well, the simplest situation, if this one is Rn, then every map is contract to a point, a constant map, because this space is contractible. Okay, so everything contractible point. That's all you need. Okay, the target is contractible. There's only one such map. If everything is up to homotopy, it's a constant map. Okay, so the reason is the target is contractible. Well, same if the domain is contractible. So it's behave like a point. Okay, so the next simplest thing is this is a sphere, which is just Rn plus a point. I just use P already. Infinity, okay, if you like that. Okay, this is the next simplest thing. And first of all, you see that if P, this is still just a trivial thing if P is very large. Because if P is bigger than N, then any continuous map move a little bit, become a smooth map up to homotopy. Then most of the point is not in the image because of Sar's theorem. Okay? So therefore, you miss one point. Once you miss the point, then you don't let the map to Rn. That's contractible point. Okay? So that's obvious. Yeah. So we try to understand what happens if you look at this to SP, where P is less than or equal to N. So this is where Pontryagin theory is. That gives you how to understand this. Okay. In particular, when P go to N, this group is exactly integer. Okay. All right, let's do that. So this will do including P equal to N. Okay, so now you have this map from M to P to SP. And then, all the argument is you look at a point, look at this pre-image, you count how many points. But now the pre-image is not 0 dimension. So you just count that. Well, it depends what you mean by counting that. Anyway. All right, so take a look. You have just choose a point here. Any point, X. Okay, this is a bigger dimension space. Okay, and then look at this pre-image. I call this map F, let's say. Okay, look at this pre-image. Basically, you want to count them, whatever that even means. Okay, and what do you know of having a map? Look at this pre-image. Well, the thing is that you choose a regular point. Okay, so regular, meaning that the map is nice, the fiber is smooth, and so on. If it's regular, all the nearby points are regular. These are open conditions. Okay, the bad point is somewhere. But once you're regular, the whole neighborhood is regular. So the neighborhood looks like this. Okay. Meaning that the normal bundle here is identified with the normal bundle downstairs, which is just one vector space. Okay. So the first observation is the normal bundle is trivial because this is a pre-image of a map to a lower dimensional space. Okay, so the first observation is trivial. So that means that you get a trivialization of this across some vector space. This space is just a tangent space downstairs. So it's P, sorry. Well, I write in this way, this is what we call a framing. It's such a fixed trivialization is called a framing. Okay? Such a thing is called a frame. So you already make this choice, it's already framed. Okay? It's a trivialization of certain bundle. In this case, we care about the normal bundle. So it's a frame submanifold. Okay? So now this is a frame submanifold inside M. Okay. Well, for example, it could look like this. So if you choose two different points, X and Y, for example, inside this gigantic space, M, the pre-image may look like a circle. This one look like a circle. Okay. But then if you move to a nearby point, there will be another circle, and so on. Okay. Well, you may hit somewhere which is singular. Okay? So here is a typical example. It could look like a product, maybe a cylinder, but there may be a hole here. It is possible. Now, the thing is, you can still assume that this one is smooth. How do you argue that? You argue the whole time, so this bigger space move the whole bigger space, okay? So if the whole thing can be, well, by moving the F, for example. By moving an F loop, you can make this whole space to be smooth, but not every pre-image is smooth. Okay? Just like if you have a map to here, you can make sure most of the point the pre-image itself is smooth. Okay? But in the whole one parameter family, you cannot argue that each fiber is smooth, or just like this. But you can argue the whole union of those are smooth, okay? By using the same SAS argument, but in one more dimensions. Okay? So they could look like that. So such a thing is called, so you also, because downstairs, maybe downstairs like this, downstairs is a sphere, you choose 2 points, x and y, and then you choose a path downstairs. Okay? And that is pre-image of the path. You can choose a generic path, the pre-image of the whole generic path is smooth. Okay? So given x and y in SP, which are regular points, okay, there exists a regular path joining the generic path is like that, x and y, such that F inverse of the whole path is smooth. Okay, it's the same type of SAS argument, like this. Okay. And you still have also the same argument. The normal bundle is just doing this. Okay, meaning that this whole thing is frame. Okay, this whole family is frame. You get a so also this whole normal bundle is frame of this pre-image. Is trivialized. But this is one less dimension though. Okay? So such a thing is called frame coordinate. Forget about framing or something. What is the cobordant? Cobordant meaning that you have one bigger dimensional space, smooth bigger dimensional space. So you have two boundary components. One is one given one, the other is the other one. And then we said that two is called cobordant. Okay? The whole theory is called cobordism theory. Okay? And we're looking at cobordant inside the big M. Right? All these are inside M. Everything is inside the fixed space M. Okay? So the point is whatever you call before called degree is this thing that you're sending M and you map here, like here, to all the frame submanifold dimension n minus p, so n bigger than or equal to p in M, up to frame cobordism. Okay. The same type of argument as before, moving one parameter family, you get a well-defined so-called degree map. Okay. For example, if P equal to n, okay. So you are looking at inside the space M, which is n-dimensional. Then you are looking at zero-dimensional submanifold in M, right? So they are just points. Zero-dimensional submanifold. Framing, in that case, will corresponding to a plus or minus sign. Because it's a trivialization, And all trivialization is the same up to GLNR. And there's only two connected components of GLNR. Okay? That's exactly the orientations. And so therefore, if you are in zero-dimensional space, you identify the normal bundle, which is a tangent bundle at that point, right, to a fixed Rn. There are only two choices, up to GLN, well, up to continuous change. Okay? So framing of point corresponding to an element in pi 0 of GLN R. So the two components determine is positive or negative. So corresponding to, you either assign to be at +1 or -1, basically. Okay? So therefore, if you, in the zero-dimensional case, the framing is just assigning sign, not positive and negative. Okay. But once you see that one positive and one negative, you can join by path, then up to frame covariance, you can cancel them. Okay? You can put them together and cancel. And so therefore, up to frame covariance, you will left with just some number of points which are either all positive or all negative. And that's exactly our degree before. Okay? So therefore, if n equal to p, this whatever degree that we call it here is exactly the same as the degree we define as an integer in that case. It's the same definition. So it's just a generalization of the degree. Okay? So therefore. Now the statement to prove is this is isomorphism. Okay? So in particular, that implies this Hopf theorem that this is isomorphism. This degree, I think. Maybe better write, it's so important right here. It's a pre-matrix. It's just mapping for all the map from Mn to Sp to all the frame submanifold in M of dimension M minus P up to frame covariance. And the statement is this is an isomorphism. So there's a remark before I prove it, just a remark here. Well, the first one I just says, just remind you some of the things I already just told you. If P is bigger than n, then this one is trivial, as I mentioned. And then this theorem is saying that at least when P equal to n, this is exactly the degree which classify all the maps. So mapping to sphere is exactly completely classified by degree. Okay? Now, if P is less than n, well, that is a theorem of this. It may not be easy to describe all of them. Okay, it's just all frame submanifold. How do you describe all of them? Okay, but one case is easier. It's P equal to 1. This is just H1 of M with integer coefficient. Well, the reason this two is easy because this is you're looking at zero-dimensional space inside M, and then they're moving in one dimension. So those are very simple to describe. This is describing codimension 1's space inside M. And they both are relatively easy to describe because it's either one dimension or codimension 1. Okay, so that's why we can describe it. And the remark is really just explaining that. Okay. So if you have a map here, take a map here. Okay, then the map will give you. Okay, so give a map. from M to S1. Okay, then the pullback from S1 integer to H1 Z. And then this one is integer, and the element we usually call it d theta. Theta is the coordinate on S1. Okay, and you just send it to pullback of d theta, or d of the. Okay, and that's the map. Okay. Now the question is, why is this isomorphism? Okay. So let me construct the reverse map. Reverse map. And then you can just check that they're inverse to each other. Okay. So give an element here. Okay. So pick an element here, call this phi. That is a lattice inside H1 of M R. Usually, if you look at high cohomology, then you may have some torsion element here. The torsion will go to 0. But H1 has no torsion. You can use a universal coefficient that H1 is related to H lower 1 with torsion of H0. There's no H0 has no torsion. So H upper 1 has no torsion. H lower 1 has torsion. H1 has no torsion. So this is really a lattice inside here. So now you think about this as so now you can think about phi as really a closed one form. I'll explain more about the round theory later, but let's assume that you already know it, which is closed. Okay. See, the thing is, you want to write as a closed, this is d theta. D theta is really a closed one form. This is not really exact because theta is not really well defined. Theta is only well defined up to integer, or they will be using here anyway. Okay. So anyway, we'll do that later. So anyway, here this is one form. It's being closed. So therefore, you can just integrate. You pick any background point in M. Pick a background point in M. And then pick any other point, you just integrate along a path. Okay? In general, depending on the choice of the path, I'll take it on the universal cover. Then it will be independent because the form is closed. So that is well-defined map because it is independent of the path up to continuous deformation, that's closeness. Not up to deformation, continuous Q by universal cover. Okay, so you get a map. Quite F tilde. And the thing is, this one is defined over integer. It's exactly saying that descends to the quotient. Okay. Because the ambiguity will turn out to be exactly integer. That was the condition integer here. And you see that this exactly will be given by the theta. That's why the pullback will be theta. Okay. So that's obvious that these two are inverse to each other. But for other cases, it's not so easy to give an explicit description of all the middle dimension thing to cobordant. Okay, so let's just prove it. Proof. Okay, let's first try to prove that this is surjective. Take a submanifold. We want to construct a map. Well, how do you, if it's submanifold, how do you construct a map? Right. So now you have some, I don't know what the manifold look like, some space M. Okay. And what you do is the following. You have a submanifold. Oh, it's not very nice. That's just with smiling. You have some submanifold. Yeah. Okay, so choose some frame submanifold. N, Y, okay, Y, okay, of dimension n minus p, which is a submanifold in M with a trivialization of the normal bundle. So normal bundle is trivialized, it's a product. The normal bundle is a product. So the whole neighborhood is really at Y cross out some N, some dimension N. Okay. All right, so you can map this point, this Y to a point, and then this whole neighborhood to this. What is so frame meaning that the normal bundle is Y cross RP. Okay, you just send it back to RP then. That's the map, RP. Okay, this projections. Yeah. So, which is the same as the neighborhood. So we are using the neighborhood film that the neighborhood is a normal bundle. Okay. So the whole neighborhood will map to RP. And you just add one point then. That is SP. All you do is you send everybody else to the point. Or you just do some cutoff or something. So basically, all you do is you send the rest to the point. Okay. And then you perturb a little bit. Because all of this is already very close to the infinity. Okay? And then you just, in the neighborhood, just squeeze everything to infinity. That's the map M. Okay. So perturb a little bit and then send everything else. Okay. To the point infinity. And then you get this map out. And they clearly have the property that this, you move a little bit to make it smooth or something. Okay? So anyway, the pre-image of this point is exactly Y. Okay? So that proof is surjective. Okay. So you, a priori, you say, well, how do you construct a map? Why M can be so complicated? You don't care. They all send to a point. Because the sphere is very simple. There's only one sphere, which is really Rn plus 1 point. So it's just everybody complicated things send to a point. You just left it a little bit. Okay, that's the map. Yeah. Yes?
The map is only assumed to be continuous, not necessarily.
This doesn't really matter because it's a homotopy class of map.
But on the right-hand side, you consider submanifold. Is it always a smooth submanifold?
No, you start with any map, you move a little bit to make it smooth. It's always assume smooth. Because it's all, so this whenever you look at the map, you just move it a little bit to make it smooth. So we look at all these arguments, assume it's smooth, but it's up to homotopy, so it doesn't really matter. Yeah. And how do you prove injective? If you think about it, it's kind of the same type of argument, move up one more dimension. Okay. Yeah. So let me skip that one. So if you understand this well enough, then you understand the injective argument, basically. Because the injective is to make sure that you want to construct what? Well, if this one map to 0, you want to say that this comes from a bigger map, something, right? How to construct that? Well, this is the type of argument to construct that in a way. Okay? So that's why they're essentially the same argument. Same type of logic, basically. Okay? Okay, so that is Pontryagin theory. And that has So very nice if n is p equal to n. That's very nice. If otherwise, this is it. But we don't know what that is usually, right? Thom theorem is amazing that if you try to understand, not this, try to understand the following thing. This is reduce the problem to understand all submanifold in M of some dimension with something. Okay, it's complicated. But if you look at not submanifold, they're just abstractly things up to cobordism. Okay, forget see that inside any particular one. Just fixing all manifold up to cobordism, because there's no submanifold, there's no frame anyway. Right? Just look at all manifold. Sorry, not submanifold. Now, all manifolds up to cobordism, you can compute it all together. So that's what Thom's theorem said. Okay, I'll show you how that amazing statement after the break. So I'm going to explain the Thom cobordism theory, the beautiful theory. So it's to compute this ring of all possible space up to cobordism. It's quite surprising. We kind of classify manifold up to diffeomorphism, but you relax that to be cobordism, it's completely computable. Okay, so look at this is the set. Call this M. So this is all closed manifold of dimension n up to cobordism. Meaning that you have a dimension M, another space. If you find a bigger dimensional space with two boundaries, one is M, the other is M2, and then they are called cobordism to each other. Okay, so this relation is given by that. Okay, if you allow this relation, this is computable. Okay? And you can compute the following ring in the sense that this has the following structure. You can take the union of two manifolds, and then you can look at the product of the two manifolds. Okay? And that gives you a ring structure. Well, not because the product will change the dimension. So you have to take a direct sum of all of them. Okay? And this is a commutative ring with identity. What's identity? The sphere is identity. So why is that? So each n itself is the abelian group already. Well, no, sorry. I should first say that if you just look at this one with the union, this is abelian group with identity. The product gives you the ring structure. The identity is the sphere. Here's the reason. If you have a manifold M, it doesn't matter how it looks like. Okay? And look at product with 1. This is just saying that M is cobordant to M. Nothing. Okay? Take any point here. This whole thing is n plus 1 dimension. Take any point in the middle, take away a small ball. And the rest will be a sphere of dimension n. Okay? So the M, you look at M cross identity minus a small ball. That gives you a cobordance between M and M with its sphere. Okay, there's no three component boundary. You think about both of them as one boundary, and this is the other boundary. Okay. Yeah. It also tells us that 2m is Sn and so on. Okay. Yeah. The Thom's theorem says the following. This ring all of them. This as a ring is the same as this one with infinite number of generator with the following relations. Okay, where each of the dimension of xn is n. So for each dimension, you have one generator, except the dimensions cannot be 2m minus 1. Okay, and then you don't have that element. And then the middle dimension one, the even dimensional one, we know exactly what they are. This is the RPN. Okay, everything. We know the whole ring. Okay. Before we do that, let me recall. So this is, amazing statement. This is just, all manifold up to this equivalent relation. You can completely determine it. Much more clean compared to Pontryagin statement in a way. All right. So before we do that, let's just recall one of statements. Things that we learned when we are trying to do this embedding, Cordero embedding type thing. If you have a vector bundle over any space, what do you call it? X, okay. Call it B, sorry. Call it B. If you have a vector bundle over any B, then in fact it comes from a universal vector bundle. Okay, so this is if you look at whole R-dimensional space inside n dimensions, so this is all R-dimensional subspace, linear subspace inside a big Rn. Okay, so by construction, every element is a R-dimensional subspace in Ln. So in particular, it has a tautological bundle, which I use the notation. I also use this notation. Maybe I should not use these notations. Like, I don't forget it. So take any vector bundle. I have it comes from a tautological bundle as long as you are making n large enough. Okay? As the argument was you can choose some local chart to trivialize it, and then keep on adding it, okay? And then you get this embedding. So embedded one. This is the argument that we had before, and so that this bundle is really the pullback of that bundle. Exactly this bundle. But that was the earlier instruction. We're going to use this. All right, so let's start. See what the notation I use. Okay. Use M. Okay. Okay, I start with M, n-dimensional manifold. Okay, and then you put it inside a very gigantic space. Otherwise, how can you do anything? You have to put it inside our n for some large n. We don't know what n is it, so I don't care eventually. You put it some big Rn, so you call it n plus r. Okay. And you can think about this, anyway, it's a closed manifold, sit inside some ball, or just think about it sit inside the ball or something. Or it doesn't really matter. Let me draw a picture. And so you have some space M, and then you put some Rn, or the ball, whatever, ball or Rn. Some gigantic space or gigantic ball, doesn't really matter. Now you have a normal bundle. Again, we use this argument that the normal bundle is the neighborhood. Okay. So Bn plus R contain this neighborhood of M in Rn, okay, which is the normal bundle. So this is a vector bundle over M, whether the way we set up the fiber is Rn. Right? So this is Rn here, Rr, sorry. So vector bundle over here. So you can put inside the Grassmannians of R inside this particular space, because now each of these is really a R-dimensional subspace in Rn plus R. This is really fixed vector space. So this is really in n plus R. Okay. So the first step is to choose any essentially. Okay? Choose any embedding. And then we do that. And this normal bundle is this tautological bundle. Pull back, right? Pull back. All right, so you set M sitting inside this Grassmannian, and then the image maybe is a small set here. Let's draw like this. And then you have this gigantic bundle, E, where the fiber is R. So the Simon said that this M is sitting here. And this bundle is really, this bundle was restrict to that. Okay, so this is this f of n, f of the neighborhood. Look like this. You add a point here called infinity. We also add a point here. It's called infinity. And you send everything there. Send all the rest to here. Because you already, this image is already going all the way here. And so the rest is all sent to the limiting point there. You missed any of this, but that's okay, because they're already sending all the way here. So F will go from M. So this is the it's like the Gauss map. It's exactly the Gauss map. You send all the normal vector to the inside Rn. This is subspace inside Rn, so just send the normal vector space to the Grassmannians n plus r. And so therefore, that will give you extend to the map for the whole normal bundle, which is the same as the neighborhood of M. That will send to this whole bundle. So that was this part. And then extend to the map to what, and then you send everything else. You send the whole sphere n plus r. You treat it as the ball n plus r. This plus the point, and then this is you write as the neighborhood of M inside the ball plus the rest. Okay, and then you send this to E, what's this? The neighborhood, and then the rest send to the infinity at the point here, the infinity point here. Okay. That's well defined because you already sent the ending point is already very far and close to the infinity. Okay. So that is continuous map, smooth it, smooth it. Okay. So that gives you a map from the S n plus r to this space, which is this point disjoint to infinity. That's called the Thom space. Thom isomorphism is the way to compute this homology. But we're not computing homology, we're computing the homotopy group. So let me recap what we had. Given an n-dimensional manifold, okay, I use this construction to get an element inside the n plus r homotopy group of this Thom space, where the Thom space is this. This is the universal bundle of Grassmannian of R n plus r. Okay, and then the map was just embedding this inside R n plus r. Okay. The statement is the claim is this whole. So this is all this space up to cobordism is exactly this map here, or this map here. Okay, this n plus r. But E, of course, depending on n and r too. Okay, maybe I just write it E r n plus r. Okay, r n plus r. Just remember this. Remember n plus r. Thom film said this is an isomorphism. Okay. The argument is very similar to Pontryagin argument once to that. But then the second part is to compute this homotopy group. And then you have to we'll describe this as type of argument later, how to compute homotopy group. Okay. A homotopy group individually is extremely difficult to compute. This is a stable homotopy group. When R is getting very large, that become computable. It's not, individual one is difficult to compute. Asymptotically, it's easy. So I will not do this today. I mean, this will be quite a different technique, homotopy group. So move it. Which one to prove? Surjective is, okay, let me just say. You just take a pre-image, basically. So you already have this space. So you have a sphere, n plus r, okay? You map to this space. This space is Grassmannian, r, n plus r. And then you have some bundle. And then you have a point, right? This space is called E Tom space. So this is E, R, n plus R. Tautological bundle, E, R, n plus R. Okay, and you just look at the pre-image of that. Smooth it out a bit, and then okay, and then just define yeah. I divide that map here and but here the way is was just trying to define that. Also worried that why this one is you have to perturb this a little bit to make this smooth. So, that was all of them. The question is why is this smooth? Well, why is this injective? Okay, so let's if you're given this map, you're given already a sphere. You think about the sphere as n plus r. Maybe I should say the following first. Yeah. Why I do this is the following. Okay. There's several ways of describing that. Is that if you have a space R n, okay, this is R n. Okay. How to describe Sn? The Sn has several ways to describe it. You can write Sn as Rn plus the point at infinity. That's the first way of describing it. Okay. You can also write this as the ball outside the boundary. So you look at the ball, n, and then identify all the points in the boundary of the ball. Okay. So instead of this, you just look at the unit length one, and then you identify all the boundary points, or you can identify everything outside something. Okay. Or you can identify which as whole Rn, and you identify all the things which are length bigger than equal to 1 at the point. I mean, identify everything else to be a point. Okay? Any of this is the way to describe a sphere. Okay? I'm going to just use this one. So an element in pi n plus r t of E r n plus r. Okay, you can think about this, the sphere in this particular way. That means that you have a boundary of a ball. There will be sphere n plus r minus 1. This is the boundary of b n plus r. Okay, the boundary. And the other one too, this is the Grassmannians, R n plus R. This is this whole bundle. Okay? And this is less than equal to 1. And then this whole thing is this one equal to 1. The length equal to 1. So the thing is you're sending all this to here. Okay? The rest sending somewhere here. Okay? Is that okay? So earlier I was saying that the Thom space is E together with a point at infinity, or the same as all the things above 1 identified to a point at infinity, right? And then this is all the thing outside, we will send it to all the thing outside here. We treat that to be this in the boundary. Okay? So an element here is the same as, because the Thom space is also like that. It's, this, so you can write down the Thom space of E. You can treat it as all the points up of length less than equal to 1, and you identify all the points equal to 1 as 1 point. That's the same argument. Okay. So now an element here, map F, is you have a map F from the ball to all the length less than equal to 1, then the sphere map to that. Okay, so this is the picture. So you get the sphere. And then you have a ball. Okay. And then you send to this Grassmannian. And then me. Or you can think about a point at infinity. Okay. So you know that all this thing will map to this one, or the point at infinity. Either way you think about it, it's the same. Okay. But there could be more points sent to infinity, though, or this one. Okay. So let's say these are also all of this. So this has to be sent to this one. Okay. But there are also more points could send to that one. I'm not saying that it has to be connected. There's just some more points. Okay. So all this will be sent to either infinity or E equal to 1. Okay, put it this way. There could be more points there. Okay. So the rest here will be U. Let's just call this, the rest is called U. Okay. So U will send to this one. Okay. So you get a map from U to send to E, or E less than or equal to 1. So either use and then you make it perturb it, so that transfers to the zero sections. Okay, that is how we define M. So that's the definitions of the surjectivity argument. Okay, yeah, more precisely. So the rest of the argument is rest of the proof. Using exactly the same technique in the point judging in the proof of Pontryagin theorem. So it's similar. So let's give a remark here. This is called a Thom isomorphism. Is if you have a vector bundle over B, okay, then you can define the following map: phi n for each n, okay, n plus r of the Thom space. Again, Thom space is just E adding a point. Okay. To the n homology of B. Remember, this is the kind of thing that we want to compute. Okay. And if for small n, this is isomorphism. Thom isomorphism. But in the way we construct things, we're just letting L larger and larger because we're embedding the space inside bigger and bigger Rn. So N is eventually very, very large. So this becomes not an issue. Okay. So that's why I can compute the homotopy eventually. By computing the homology of the glass magnets for large enough R. Okay. So that's a technique to compute those. So let's say variant of Thom's theorem that is even nicer. Yeah, same type of technique. And then if you look at instead of looking at all manifold, you look at oriented manifold, assuming all the coordinates are oriented. Everything is oriented. And if you are this case, and if you are taking away the torsion part, so this ring you tensor, is over integer, you tensor over Q. That is very simple to describe. That one is a ring over Q that has generated exactly all the even dimensional CPN. Exactly all of those. No relation. Yeah, that's it. That's that. Okay. Yeah. Okay. And there are other things like yeah. So that would prove the following. Okay. So it's a corollary. Okay. So if you have a smooth oriented manifold, okay, if this is cobordism to 0, okay, that means that if this one is the boundary of some x, where x is also oriented, okay, well, that means that there will be element 0 here, okay, but this is 0 up to torsion, okay, so you is true up to, for some k, okay, that means to kill all the torsion. Okay. If for some k this is true, okay, if and only if it's 0 here. Okay, you want to check that, one way to check all of this is in fact to check all the Pontryagin number, and yeah, if and only if all Pontryagin numbers are 0. So that is so-called characteristic classes. You look at all the combination of characteristic classes integrate, and then one of those characteristic classes are point-judging classes. Okay? So point-judging number is just you look at various point-judging classes of M, could be I1, I2, any such possible combination integrate over M, and those are any of such are called point-judging number. Okay, so they can be usually computable. Okay? So the point is these are very easy to compute. Okay. And so it's very easy to determine when a manifold, at least up to several copy, that is a boundary of something in the oriented case. Okay. In an oriented case, you also have the Sniffer-Winnie class number and so on. So anyway, all of those are very easy to determine. So this is why it's just such a powerful, beautiful theorem that it tells us that you know exactly classify all the space up to cobordism, and not just up to that, it's computable. Okay. Yeah. So that was the type of argument was used, but eventually you have to compute the stable the cohomology of glass Meinong for a large range where R is going to infinity. Okay? That can be computable too. Yeah. That's how to prove the theorem. All right? So that's chapter 3, I'm going to prove the Frobenius theorem. Another famous theorem in manifold theory. So given a manifold M, among other bundle, there is a specific bundle which is different, which is a tangent bundle. Okay, this is very special, mainly because of the following statements. We have the following statement that if you have two vector field, that is a section of the tangent vector bundle. At each point, you have a vector on the fiber. That's what they call a vector field. Okay, and then you can construct another vector field. Locally, so that is the main thing which makes tangent bundle is different from other bundle. Okay. So locally, meaning that you choose a coordinate, so you can assume that locally look like Rn. And then locally, the vector field will be summations of some functions, I from 1 to n, ui, x1 up to xn, dd, xi. Right? Locally, you can write vector field like that. And do the same thing for v. And then you just do whatever it is. So UV is the following. It's just summation of UI dxi. I'm just going to write as dxi here. Okay. So it's you should think about this as just a UV minus VU. So what does that even mean? Okay. These are not functions, these are vector field. Okay? So UV refers to summation of UI dxi on summations of Vj dxj The other one is similar. Okay, but this is dxi dx3 is not a vector field, but dxi is a vector field, and so therefore when you but then you just pretend you just don't know what you're trying to, you just differentiate. So if you differentiate this one, differentiate, you have two terms. One is dxi vj dxj. The other one ui vj dxi dxj. Okay, and the other term is just exactly the same, just switching u and v. Okay, and then the other term will be minus is vi dx. It's just switching u and I, or I and j. Right? So this is this j dxj v I u j dxi dxj. Okay, so this is a vector field. This is not a vector field, except this cancel. Okay, summation over I and j. So now it becomes a vector field. Okay, so therefore this one is just ui dvj dxi minus vi duj dxj dxj, sum over ij. Okay, so that is and the point is that's well defined globally. Okay. Another reason of having such a thing, such structure, this follows from the following fact. What is a vector field? Well, a vector field looks like this. It can be 0 or can be 0. Okay? If you start with a vector field, you can start to move along the vector field. Okay? Giving you a vector field. Okay. So, and this is an ODE question. That's why you can always solve it. So if M, let's say a closed manifold, otherwise compact without boundary. Okay. Then the ODE can have solution for all time. So solving ODE, you can just compute this flow. So you get a function from M cross R to M, satisfy for whatever. Meaning the following, you just draw the picture. So you start with M, you have a point in M, and then after time t, and then you just using this flow to integrate the flow, and then you measure what happened after time t. Okay, solve the flow. Okay, suppose everybody know this. Okay, so get this flow. It's called flow generated by V. Okay, so every point the flow will give you. I mean, the whole space will be flowing this, like one-dimensional. Some of them can be coming back, and you keep on going around and around and around. And there's also some point could be just stable. Let's say the vector field is 0. The flow doesn't never move it, you just stay there. Okay. So if V is never 0, not managing. If V is not vanishing, then you don't have point. Then the whole space is just a union of one-dimensional subspace. And foliations. Okay. If V is non-vanishing, it gives you the following. This whole, all the direction generated by V will be a subbundle of Tm. Okay, rank 1 subbundle of Tm. Okay, and these are called distributions. And the Frobenius film, which is extremely useful in geometry, says the following. Notice that this one, you can do all this because you're solving an ODE. Why is this ODE? Because you only have one direction. Okay, then you can always just go along the flow line and then flow it. Now the question, if this is not one dimension, the film of Frobenius is if the tangent bundle of M has a subbundle of dimension, doesn't matter, R, let's say, okay? So any subbundle. We just call it distributions. So if you draw the picture, it means the following. You have some manifold, and at each point, you have some fixed subspace inside the tangent space. So this is called a distribution. Every point in the tangent space, you have some subspace of some dimension. Okay? And the dimension of the subspace is called R. So each tangent space, you have an R dimensional subspace inside the tangent space at that point. Okay? Smoothly. Okay? So that's called a distribution. The question is, when can you integrate it? Okay? When you can solve the PDE. Okay? So you get a that's called a foliation, meaning that you can write a more precise statement, but let me draw this is up to the smoothness. That's how you say it. You write the M as disjoint unions, many of those, of some inside some leaf space. Okay, leaf space. For each of that, you get some, maybe leaf. Leaf is F, maybe. Leaf, L, leaf. Okay, leaf, some leaf. Okay. So these are all. So all this is a disjoint union of R dimensional submanifold of M, such that for each point in L, the tangent space of that point is exactly the distribution at that point, meaning that you can find submanifold, not just at each point, really submanifold. M is a union of submanifold of same dimensions, okay, such that these are the tangent space of that point. Okay? To be more precise, you really have to write local chart to say something like that. But that is how you think about that. There's some smooth topology making it as union of such submanifold. Okay. The statement is this, because now this is really solving a PDE, because you're solving two directions, or R direction rather than one dimension. So of course this is extremely difficult. And the statement is this is true if and only if the following, okay? For every UV, which is a for any two vector field, it turns out sitting inside this distribution. So there's supposed section of Tm. Let's suppose they sit inside D. Then the bracket, because they are vector field in M, so the bracket is still a vector field in M, but you also want it still also sit inside that. And that's a necessary condition, because if you have a submanifold M on L, and then on L is already satisfied, because it's a manifold. So that's a necessary condition. The question is, this is sufficient condition. Okay? And such thing is called integrable. So if you get integrable, you can integrate, and then you get a foliation. That's why I call integrable. Yeah. I should not skip that one. Okay. Yeah. So that's a Frobenius field. It's highly non-trivial to really do that. Okay. And it has application in many, like many has complex structure and things like that. Okay. Any questions so far? So this I will prove it to you next time. There is another situation which is much harder. It's a complex integrability conditions. It's a much harder field. And that's, let me say it that way. Yeah. Remark. Nuremberg film. Will tell us that when M is a complex manifold. So you have I'll explain, say that more precisely next time. You can describe the complex structure in a way like a foliation type structure. Okay? And then you have, then the integrability will be checking some condition like that. Okay? And to prove it, that statement is an amazing work by Nuremberg using PDE. But that is take longer to explain that. Yeah. And one more remark I want to say before I end today is okay. The question is why do you have this on section of the tangent bundle? Okay. But the statement is given a vector field and then I create this map F, which is really a map from M to the diffeomorphism group of M. Right? This map from M cross R to M. In fact, once of this is really diffeomorphism because it's a moving point around. Okay, the diffeomorphism. Okay. And in fact, V will be just dF by T, dt, and T equals 0. Was saying that vector field is exactly, well, you can obviously see what a vector field is. If you have a diffeomorphism, you're moving point around, that's what a diffeomorphism. If you only move a little bit, that's what we call a vector field. That's just the first step of moving, right? Everybody here, you know which direction and how fast you start to move. And that's what a vector field is. So that is an infinitesimal diffeomorphism. So this one is a tangent space of the group of diffeomorphism at the identity. And so this is sometimes called the Lie algebra. And it's a group structure here that gives you the Lie algebra structure here, which is a bracket. And there's a bracket here. Okay? So This is an intrinsic reason why the tangent space has a bracket, because this really comes from symmetry. Symmetry is a group. The group structure is the Lie bracket structure, the same structure. Okay. Yeah. All right. So maybe I just stop here, and then we'll prove the Frobenius theorem next time. Any question?
What happens when the rank of the distribution is not constant? If there still have a formation?
Okay. So see, the thing is, what do you mean by that if you are in the smooth category? Because when you are jumping, usually in the smooth setting, you are looking at subbundle, right? If you start to jump, then how to describe the topology of how things are called smooth and they jump? You can say that more precisely in algebraic geometry, because jump and then as a coherent subshift. Okay, yeah. And people do talk about in algebraic geometry, people do discuss like foliation pentagram jump in that case, but it's a much harder situation. The thing is, this theorem is not just nice and looking here. It's an important application in real life. Like if you study the Lie group theory, doing this kind of thing, you really need the integrable this theorem to give you the all the structure of the Lie group with relation to the Lie algebra structure. So it's more practical in this case. The singular foliation, meaning what you're trying to ask, they did use in classification of algebraic variety in some way, but hard to say anything in the smooth case. Yeah.